is. And the nucleation is a very important part of solidification, where the grain growth and the solidification process actually initiates. So let us start with the lecture. So first thing that I want to discuss with you right now, is basically the concept of cooling curves. So what is a cooling curve? So cooling curve is basically a line graph which represents the change of phase of matter from gas to solid or liquid to solid. Now this variable that you see over here, that is time, and the second variable that is there is called temperature, and it is a graph between temperature and time. The initial point of the graph, that is this point, it is called as the pouring temperature, and this part is called as the freezing process, where the liquid, as it cools down, it is start to lose its heat and generate and starts to convert the process into solid. Now this is what is called as the stabilization zone, or the freezing temperature, or the melting temperature, TM, or it is also called as TM.
Welcome
or it
to
is called as the
Camtasia.
freezing temperature.
This sample project will
Now
provide
for
a quick
freezing
tour and
temperature,
get you started.
this is the point
If
where
you're
the
looking for more
freezing
in-depth
actually
tutorials
starts,
that walk you through the entire
and this is
process
the
of recording,
point where the freezing
editing, and sharing
actually
your videos,
converts
check out the
it
video
into a
tutorials
solid.
on our website.
So this time
And if
is
you want
called
to
as the
open a
local
fresh copy of this
solidification
sample
time,
project, you
and
can find it in the Help menu.
this is called as the local
Right now,
solidification time.
you're in the Camtasia
and
editor. The editor is made up of the
other
timeline,
part
where you can
is called
arrange
as
and
the
edit your
total
clips,
solidification
the
time.
canvas,
The other
which
part
is
is
your
called
video
as
preview,
the total
and the tools
solidification
panel,
time.
where your media is stored,
So
along with
what you are
shapes,
seeing over
animations,
here is
effects,
basically
and more.
something which is
At the top of the Tools panel,
very
there's a button
important
to launch the
for
Camtasia
the
Recorder,
purpose of
a tool that captures all of the action
solidification,
on the
because
computer
the
screen.
internal energy which is utilized for converting from one state to the second state is being transferred over here,
When you're done recording,
and this energy is called as
each clip
the
will be placed in
latent
your
heat.
media
So
bin
this energy is called
and
as
on your
the
timeline.
latent heat.
If there are
And
parts of
this
your
is what
recording
is
you
called
don't
as
need to
the
show,
cooling
can
rate,
trim them
where
from the
cooling
end.
rate is the slope of the cooling curve at any given point of time.
or cut them from the middle.
Now, because what happens in the cooling curve for a pure metal, the chilling action
If
actually
you'd like to add
starts
other
from
media,
the mold wall
titles,
and
or
proceeds
effects,
inward
drag
into
them
the
from the Tools panel
liquid molten
to the
metal.
timeline.
So what happens is the
If you
section
choose
which
an
is in
effect,
contact with
such
the
as an
solid
animation
wall
or
actually
transition,
starts to
the clips on the
generate
timeline will
a
highlight,
skin
showing
of
you where it can
solid
be
metal,
applied.
which basically creates a front
While you're working
for
on your project,
solidification, which
use the
proceeds
canvas to
inward into
position
the
your
system.
media
That
and
generation
preview
of
any
this
edits you
front
make.
is actually dependent on the
You
rate
can
at
use the
which the
Properties panel to
freezing
fine-tune your
process
media
is
and
taking
effects,
place.
such as
The freezing
positioning an
process is
object to
taking
an
place.
exact
So
location,
what happens over here
rotating
is
an object,
that this
or
rate
even
of
changing
freezing
its scale
process actually proceeds
and opacity.
accordingly to the
When you're
thermal
satisfied with
properties
your
of the
video,
metal that you have
export
got,
it as
the
a
thermal
file on your
properties of
computer,
metal that you have got.
share
So
it to
the
popular
freezing
web
rate
destinations,
actually defines the
or
growth
upload
of
it to
that
video
thick
review,
skin.
and invite your
Now
colleagues
the
to
metal
review the
which
video.
forms from this skin
Now it's time for
actually
you to
rapidly
try.
cools.
To get
Because
started,
the heat
experiment
process,
with
that
this
is
sample
heat
project.
extraction and heat
Try deleting or
deposition that
adding
is taking
clips to the
place between
timeline,
the front
or maybe
and
add a transition.
and the liquid metal actually causes rapid heating and rapid cooling because of the extraction of heat from the mold wall. So this cooling action causes the grain which are developing in the skins to be fine and randomly oriented. They are not directionally oriented, they are randomly oriented initially. Now as the cooling continues and the front advances towards the center, what happens is the grain growth start to happens in the direction away from the heat transfer. Now if suppose this is the mold and the front is over here, now this is the molten metal that you have got. So what happens is the heat transfer is taking place over here. So the grain that is over here now, it solidifies and generates a fine structure because it is still experiences some amount of heat, which causes the grain refinement process to continue. As this front goes on moving towards the center like this grain on experiencing heat will undergo the refinement process again and again. As a result, what you get are fine grains which grows inwardly. Now the nature of these grains are basically like needles or the spines of spines basically. So these shapes is called as the dendritic growth. The shape is called as the dendritic growth, and these tree-like structures gradually fill the complete molten area, and during the freezing and the cooling cycle they converge into something which is solid with help of lateral branches as well as undirectional or unintended branches which merge together and form a solid which basically entraps liquid under itself, and after more metal pours in, the solidification process goes on, and ultimately on complete solidification it converts into a very fine solid. But the problem over here is that the direction of the grain growth and the direction of the solid that is being generated, the spines that are being generated inside the solid, they basically compress each other, they stretch each other or compress each other, thereby resulting in stresses being generated into after solidification, and as a result you need to do some post-processing operations in order to relieve those stresses and make the surface homogeneous. So what you see in figure 1 is actually the ideal cooling curve. Now this is an ideal cooling curve that you see, that the liquid phase is being converted over here, and at melting point what you see is liquid and solid phase coexisting, and after that below the melting point solid phase has started. Now this is something which is very ideal, and but when you go into practical analysis and you observe, what you actually see is a curve something like this, where the actual process of solidification actually starts from here, where the temperature goes slightly below. Now this is the melting point, so the temperature actually goes slightly below the melting point, 2 or 3 or 5 degrees below the melting point, and then comes back and solidification process starts. So this part is called as the undercooling area, undercooling zone. This undercooling zone is very important over here because this undercooling actually initiates the formation of nucleus or the nuclei, which will result in the growth of the solidification front and the solidification area. In homogeneous solidification, the pure metals actually generally undergo homogeneous solidification. So in homogeneous solidification, there is no foreign particle to initiate the grain growth or the nucleus, new formation of nuclei. So what happens is rapid cooling and rapid heating from the mold wall towards the center actually generates vapors, and these vapors condense together to form a sort of a solid. Now, this process takes a long time in homogeneous solidification. So as a result, what happens is, what you observe over there is, although the grain are very good and very fine and the stresses are not high as compared to heterogeneous, but what you observe is the process takes a longer time. So this type of a curve that you see over here right now, this type of a curve actually reduces the time which is taken for the process to initiate, the solidification process to initiate. As a result, what you observe is rapid solidification. Now, from the Gibbs free energy principle also, you can very clearly observe that at this temperature, at this point, what you are seeing, if you plot it down, what you see is that at this point, there is a difference in Gibbs free energy also. So this free energy actually is utilized for creating a nucleus, and once that nucleus is large enough, it starts the process of solidification. And but it has to have a certain radius so as to start the process of solidification, that I'll explain later on. Now, in the cooling curve of alloy, there is something different that you observe. Now over here in a pure metal, there is only one temperature, but in an alloy, there are two temperatures. There is a liquidus temperature and there is a solidus temperature. So there are two temperatures that you see over here. Now I have taken an example of 50% nickel and 50% copper composition over here. So nickel has a melting point of 1455 degrees centigrade, whereas copper has a melting point of 1083 degrees centigrade. So what happens is, this is the ideal cooling curve of a alloy, and what you see is that once the pouring temperature drops, this line is slightly more inclined, or there is a less temperature drop with respect to time as compared to the pure metal. Now why does this happen? This happens only because the difference of the predominance of a higher melting point metal over here, the predominance of a higher melting point over here restricts this loss of energy or loss of heat as compared to the lower melting point. The lower melting point, although metal will give the heat more, but it will be compensated by this metal, the second metal which has a higher melting point. So the freezing rate is slightly lesser in alloy as compared to pure metal. But the main area of concern is this, that is this zone where liquid and solid properties actually coexist over here. Now, the dendritic growth that I was talking about in solid metal, which happens during the phase of solidification, actually is more predominant and more effective over here, because what happens is that you understand that there are two metals right now which are going to coexist together. So what happens is the temperature spread that is between over here, that is the maximum temperature gap that you observe between solidus and liquidus, is going to facilitate the growth of dendritic and the advancing front for both liquid and solid to coexist. So what happens is, initially you get a very small portion of dendritic structures that have been formed. Now in the solid liquid region, what happens is you have got a solution, basically sort of a solution, which has got a peculiar characteristic. It is a dense fluid. It is not a free flowing fluid. So depending upon the condition of freezing, the zone between solidus and liquidus can be narrow or it can be wide. So depending on the width of that gap, basically you observe different characteristics of the dendritic structures that are generated during the solidification process. The wide difference between solid and liquid basically generates slow heat transfer out of the molten metal, and you get finer structures, whereas a thinner gap between solidus and liquidus generates more heat transfer, and as a result the structure that is generated is not very fine and it requires post-processing. Another very important aspect in the solidification of alloy is the composition of dendrites. Now when you have got a bigger gap, you have more heat into the system. As a result, the dendritic structures are more refined. And another aspect is that when the dendritic structure develops, it hides basically some amount of molten metal underneath it, which was solidified later on. So when you have got more heat coming out of the system, so that dendritic structure is definitely going to be more refined as compared to the short heat transfer, where more heat is being transferred out. As a result, you get more energy out of the system very fast. The imbalance between the metals that are solidified actually also define the type of structure that you are going to have after the solidification process. So if you have, that is why generally when we talk of alloys for casting, we prefer to have those metals which have slightly closer melting point as compared to something that has got a wide melting point. Like we don't use cast iron with copper. We never use cast iron with copper because the gap of melting point is very huge. Similarly, nickel is not used with cast iron also. Steel is used with cast iron or steel is used with nickel. So we generally prefer to keep use those alloys for casting which have basically got closer melting points as compared to wider melting points. So in casting, we are basically focusing on two types of solidification that we generally observe. The first one is called as the progressive solidification and the second one is called as the directional solidification. Now, progressive solidification is something where a casting is basically solidifying from the diameter towards the center. It is solidifying towards the center. So what happens is, whatever amount of cavity that remains after solidification, it remains at the center, and as a result what you get at the end is something which is a defective cast. You have a hot spot or a hot spot inside the casting which cannot be rectified under any circumstances. And that is why progressive solidification is avoided in casting processes. Now, directional solidification is something where the casting solidifies across the length of the mold where the casting is being made. Now, this type of a casting can be, this type of a solidification in essence can be very easily controlled, and the rate of cooling or rate of freezing also can be altered with the help of a device called as chill. So using chill, you can always control the rate of solidification in a directional solidification, but in progressive solidification that is not possible. But yes, in some types of castings where we want hollow casting, progressive solidification is also employed. Progressive solidification is also employed, and we get different types of configurations working at different point of time. But predominantly when we are making a casting, we are more bothered about directional solidification. Now, this is another topic that I wanted to discuss, that is the shrinkage during the casting process. So as this graph I have already shown to you, this is an ideal cooling cycle graph. What happens is that during the solidification process, the solidification process actually starts from here itself. This is the pouring temperature. So as the metal is poured into the mold, the solidification process actually starts instantaneously. Although theoretically we call the solidification process that is happening inside the mold wall, mold cavity, but solidification process actually starts from the moment you start to pour the metal. So what happens is there are three phases or three distinct areas where the solidification process is going on. This is the first area, that is contraction of liquid before the solidification of cooling process. This is the second area where the contraction is taking place during the phase conversion, where the phase conversion is taking place. And this is the third area. So this is 1, this is 2, and this is the third area where contraction of solid is happening from during the cooling to the room temperature. So what happens in the first area? In the first area, the molten metal is being poured into the mold cavity, and as it enters into the mold cavity, what happens is this mold wall is at a lesser temperature as compared to this molten metal. So what happens is immediately heat transfer starts to happen. Immediately heat transfer starts to happen on all the sides. So during this heat transfer, what happens is that a layer starts to generate at the mold wall, which is basically a thin skin of metal which is solidifying as a result of heat transfer getting balanced out. So what happens is that you get a new front where this area that you see is actually a thin skin which has developed because of the energy balance or the heat balance that has happened at this point of time. So this is the first stage of solidification that happens, and during this solidification what happens is as the solidification front is developed, the contraction, because the skin is not very thick, it is not able to sustain the huge amount of heat which is being transferred from the molten metal towards the mold wall. So that front actually experiences heat, so it expands, and as it loses the heat to the other side of the mold wall, it contracts. So that expansion and contraction actually happens. Now as a result, what happens is that the liquid in metal actually reduces. The liquid metal actually reduces. Why it reduces? Because as this area is being developed, that is the mold wall, and the skin around the mold wall is being developed, it is contracting. So as it contracts, what happens is, if you compare this height, this amount of metal has been utilized to generate the skin. And this contraction is approximately 0.5% of the total metal that was poured into it. So the initial contraction that has happened, it is basically this contraction that takes place. Now, once this front becomes solid enough, it also contracts in volume and it draws molten metal from the inner part of the casting. So once this area, basically this area, it starts to solidify and it contracts, what happens is it takes in molten metal from this side. So as it takes molten metal from this side, the height will come down. This height will actually come down. Now the third stage. So what happens in the third stage? Third stage basically takes place under two circumstances. The first circumstance reflects the contraction which is caused by further expansion of the solidification front. So what happens is, now the solidification front has exceeded to this part. Now this is the solidification front that has been developed. So solidification has taken place from the top, solidification has taken place from the sides, and solidification has taken place from the bottom. So now this is the liquid metal that remains. Now still this liquid metal is still going to cause heat imbalance. It is still going to cause heat imbalance. So the heat is going to come into the solid metal and cause refinement and of the structures that have been generated by exposing it to heat. So what happens is, first, the contraction is caused in the height of the casting, and the second is the top center portion, which is this part, basically the top center portion, which is this part. This part is going to freeze right at the end. As a result, there is efficiently going to be heat transfer going outside, that is outside the mold. So as a result, what happens is, this area that you see over here, that is going to contract at the end. Now what happens is that this wall is going to contract like this. So as this contraction happens, this area is going to have a void structure, and that void structure is actually going to cause restriction in the casting, and that restriction or the void structure is going to reflect as a shrinkage cavity over here. So once all the area has been solidified, what you observe is a cavity and a solid metal which has contracted from all these sides, As a result, what you observe is that the amount of molten metal that is required to take in shrinkage is basically going to be higher as compared to the actual volume. So that is why risers and ingates are utilized. So now what you see over here is that solidification shrinkage will occur in all the metals, all the alloys, irrespective of whatever the composition is, because the solid metal is going to have a higher density than the liquid metal. Similarly, when the phase transformation takes place, the contraction that you observe is volume per unit weight of the metal. But in case of cast iron, there is a different phenomena that is seen. That graphite starts to form, and graphite is basically carbon, high temperature carbon, which is able to absorb lot of heat. As a result, the contraction is very minimal, less than 2% to be exact, and that results in sometimes expansion also. If more graphitization basically takes place or more graphite is generated, what you observe is basically rather than contraction, there is an expansion. So solidification shrinkage will occur in all the metals, and the cavities that are generated can be controlled using different modes of uh, remedies. Like you can use chills, you can use angled irons, you can change the cross-sectional area of the casting so as to control the rate of cooling. So you can always control the shrinkage, you can always control the deformities arising out of shrinkage, but you cannot eliminate this shrinkage phenomena except in cast iron, that too where the graphitization process actually happens. So this whole concept of solidification actually is dependent upon the cooling rate, and the cooling rate is basically defined as the heat loss by the casting per unit time. And naturally the cooling rate depends upon the mold material. If you are using a metallic mold material, then the cooling rate will be higher as compared to a wooden metal, because metal is able to absorb heat at a faster rate, so the cooling rate will be higher, whereas the green sand mold or the wooden mold will not take that amount of heat, so the cooling rate will be lesser. Another very significant point to remember is that the cooling rate is always going to be higher at the beginning of the solidification. As the solidification process continues, the cooling rate becomes slow and low, and the cooling rate after some time will be more at the bottom of the casting where the metal plates are used as the base. So if you can, I'll just go back. So if you see this area is exposed to more metal. As a result, it will have better cooling rate as compared to this cross section, because this cross section only faces one section. So cooling rate basically is dependent upon the type of metal that you are using and how that basically controls the rate of heat transfer. So that is what is going to have a cooling rate. However, you have to remember one thing, that metals which have got a long freezing range tends to develop a lot of deformities also, like hot tears or surface cracks also. They tend to generate lot of defects also. So we generally use those metals which take lot of heat but do not contract or do not expand exponentially. Aluminium, that is why aluminium is not used as a mold generally, because it takes heat and it expands, so it causes a lot of deformities. And as it cools, it contracts also very fast, so it will develop a lot of surface cracks also. So solidification process basically contains of two steps. That is, the first step is called nucleation and the second step is called as the growth. Growth is something which is exponentially related to the process of nucleation. I'll explain the process of nucleation to you. What the nucleation is the process where tiny solid particles called the nuclei are formed when the liquid metal cools below the liquidus temperature. So nucleation process actually starts as we go below the liquidus temperature. Now for a alloy, the liquidus temperature is on the higher side, but for a pure metal, it is the melting point that you observe. So how does this nucleation process actually originates? Now the nucleation process actually originates in two ways. There is a homogeneous process and there is a heterogeneous process. So in homogeneous process, what actually happens is that when the heat transfer is taking place, vapors are also being generated, and those vapors which are not able to escape out of the mold cavity, they actually condense and they form droplets, and these droplets actually solidify on the mold wall, stick to the mold wall, and it solidifies and it starts to generate the solidification front over there. In heterogeneous nucleation, what happens is that there are impurities within the mold area which are utilized for creating nucleuses which will actually propagate the process of solidification. So homogeneous nucleation actually takes place in a very straightforward manner, where the nucleation front actually comes in towards the center in a uniform pattern. But in heterogeneous nucleation, this is not the case. The rate of nucleation is very fast. How different they are in terms of nucleation rate? In homogeneous nucleation, the amount of total energy that is consumed for creating a new nuclei is something in the range of 22 to 25% of the total energy. So you require a lot of energy to be consumed to initiate the process of nucleation in homogeneous. Whereas in heterogeneous nucleation, the experimental data basically shows that the amount of energy that is required to propagate the nucleation is roughly between 8 to 10%. So heterogeneous nucleation can be started very easily as compared to homogeneous nucleation, and that is the reason why in most of the castings that you observe, the heterogeneous nucleation is the actual process that actually propagates the solidification as compared to homogeneous nucleation. So for creating the homogeneous nucleation, you need to understand that the nucleus has to have a specific radius so as to start to propagate the solidification front. So what actually happens is, I'll just give you a brief idea of for that this is a liquid that is there. Now this is liquid. So this is the water molecule that is stuck to the wall, and it actually starts to create a front in itself. This actually starts to create a front in itself. Now this is liquid, this has become a solid. So this front that you see, that is a solid liquid front. This is a solid liquid front. So in homogeneous nucleation, what happens is you have got no impurities into the system. So then whatever nucleation is going to take place, it is going to take place between solid and the liquid. Another important aspect that you need to remember for this is that this nucleus can generate anywhere in the molten pool. This nucleus can generate anywhere in the molten pool. Okay, so there is no specific location, but once it attains a critical radius, it starts to grow. But before it attains a critical radius, actually it grows and shrinks. It grows and shrinks. It goes and shrinks because it is consuming lots of free energy which is available in the system at that point of time. So what is nucleation? Nucleation is said to take place only if precipitation of components from a solution reaches a critical size. And that critical size is called as the critical radius of nucleation. When it starts to actually grow rather than shrink. So as it grows bigger, the solidification front is also becoming bigger. As a result, the heat transfer is now basically taking place not over here only, it is also taking place over here also. So that is what solidification front actually looks like. You have lots of these nuclei working in different areas. You have lots of nuclei working in different areas and they are creating new solidification fronts. Sorry. So nucleation occurs at sites where the contracting liquid or the solid phases actually coexist. So when the vapors are in supersaturated state, they condense to form liquid nucleus which grows till it comes to equilibrium with the surrounding vapors. That is, heat balance has been established. Once the heat balance has been established, you can have the process of nucleation. Now, what is the shape of that nucleus? That is very important to understand. What is the shape of that nucleus? In reality, it's very difficult to predict the shape because it has got a very irregular shape. It is something like this or something like this. So it is very difficult to predict a specific shape of the nucleus that you have got. So for sake of mathematics, what we assume is that the shape is spherical. We assume the shape is spherical. And the size of the nucleus is small. So this assumption actually helps us to basically neglect the concept of gravity, which is also working during the liquid medium conversion to solid medium. So as the density increases, the gravity also starts to act on the solid particles and it starts to pull it down. Okay. So spherical shape basically helps us to, for mathematics purpose, as well as to, since the small nucleus is there, the gravity effect is also neglected over here. Now, in terms of bulk condensation energy and the surface energy that is there, we have two basic terms that are utilized, that is based on Gibbs free energy, that is basically based on Gibbs free energy, and delta GT is the total free energy change associated with the formation of solid particle. So the equation that we write in terms of energy balance is delta GT is equal to minus V upon VA delta GA plus A gamma SL, where V is the volume of the solid particle, the particle that we discussed in the previous slide. A is the particle surface area. VA is the atomic volume. Delta GA is the free energy change per atom associated with solid to liquid transformation. So liquid is being converted into solid. So that the energy for every atom, that is the free energy that every atom is going to take during the transformation from solid to liquid. And gamma SL is actually the surface energy at the interface between solid and liquid. So this is the atom. So gamma SL is actually going to be SL is actually going to be the surface energy working at the boundary over here. The free energy per atom is related to free energy change per unit volume, that is delta GV, by this formula. Delta GA is equal to delta GV into VA. Now this is for per atom. Okay, so this is for per atom, but we know that in a molten pool, one atom is not going to be generated. There would be lot of atoms which would be generated simultaneously. There would be lot of areas which would be generating simultaneously. So as a result, what you will see is that there would be multiple number of atoms. So what happens is that if we take n number of atoms in a solid particle, so delta GT can actually be written as this formula. Delta GT can actually be written as this formula, where n is the number of atoms and this is the shape factor. The shape factor is basically defined by the atoms, the atom atomic mass, basically the atomic mass that will be there, and n is the number of atoms which are there. So you will get a shape factor, and when you put everything back over here, like neta, value of neta from over here, this equation of delta GT will be converted into a simple equation. Now if you try to plot this equation, what you will observe is a graph which will look something like this. Now what you need to find out is what is the critical number of atoms which are needed, which are actually needed in order to basically propagate or basically generate the solidification process. So in order to do that, what happens is the free energy that is required for a critical number, is basically given as delta G is equal to this function, and when you convert the values of gamma and neta into the function, this is the final value that you get. So this is the maximum energy, free energy that is going to be generated. That is the maximum energy that is going to be generated over here so as to create the energy which is required for the critical radius. So now what happens is when you substitute all the values over here, you get the critical radius. Now you get the critical radius and the energy change that is associated with this critical radius. You will get the critical radius. Now what you see over here is that you have got a particle, basically a particle which has got a specific radius, which has got a specific radius, and where the critical energy that is being generated has a specific value. So what is this energy actually dependent on, or what is this value actually dependent on? The critical radius is actually dependent upon the surface energy between the solid and the liquid interface, and the Gibbs free energy that is available for the volume of atoms that are being utilized to create the solidification front. Now, if the number of atoms present is less than the critical radius, if it is less than the critical radius, what you will observe is that suppose n star is equal to 4 and you only have got 3 atoms right now. So what you will observe is that there is more energy in this molten pool. As a result, these 3 atoms will actually contract because they will take more energy, and after some time when the energy balance has occurred, still there is a lot of energy remaining around. Hence, as they solidify, they will start to contract. Now on the flip side, what happens is, suppose you have got more atoms as compared to the critical number of atoms that are required. So you have got 5 atoms, whereas the critical number of atoms for nucleation was 4. So what you observe is that the free energy that is available in the system has actually decreased because there are more atoms who are taking in more energy into themselves for their expansion. So the net energy that is available, free energy that is available, has reduced. As a result, what you will observe is that these particles will actually grow faster as compared to the previous case or as compared to this case. So what is the ideal scenario that you want is that number of critical atoms which are developed into the system should be equal to the number of atoms which are required to generate or propagate solidification. So this is all about homogeneous solidification. Now let us talk about heterogeneous solidification. Now in heterogeneous solidification, what happens is 99% of the time the nucleation initiates at the walls of the containment vessel. So this is the containment vessel that you see over here. This is the mold. Now a solid has been developed over here in the midst of all the liquid. So now what you observe over here is something very different. Now in homogeneous nucleation, there was a single front. There was a front between solid and liquid. But now what you observe, there are 3 fronts. What are the 3 fronts? There is a liquid and a mold front that is over here. There is a solid and a mold front that is over here. And there is a liquid and a solid front that is acting over here. So rather than having a single energy, what you observe is you have got multiple energies acting into the system right now. And the shape of this solid that is being developed actually defines how this energy, that is gamma SL, the surface energy between solid and liquid phase, is going to behave. And this angle theta plays a very significant role in identifying how this surface energy variation will actually take place. So now if you balance the surface energy, what you would observe over here is that this is gamma LM, this is gamma SM, and this side it will be gamma SL cos theta. So gamma LM is equal to gamma SM plus gamma SL cos theta. So the surface energy balance actually takes place in this way. And the geometry is basically what you can say is a cap. So the surface area or the volume of the cap is given by this formula. And the surface area between solid liquid front basically is given by this formula, and the surface area or the between the solid and the mold front is given by this area. So how the formation of spherical cap involves? First, liquid is converted into solid. It creates a new interfacial area, ASL, that is solid liquid, and changing the interfacial area from liquid mold to solid mold at the contact area between solid and liquid. Let me please go back and I'll explain that. Now this is a liquid. Now this liquid has generated a solid in its midst. So what is the energy change that is taken? The energy change that is taken is over here, that is between solid and liquid, and some energy change has taken place over here between solid and the mold, between the solid and the mold. So what you observe over here is there are two surface areas which are there, and this area is actually just transferring heat in through the system, in and out of the system. So this, the final formula that you generate is this, and when you solve this formula you get this function. Now if you remember, this value is similar to what we obtained in the homogeneous solidification front, but this constant is something which is different. This is something different. So what you observe over here is that S theta is actually a constant which is governing GT. So if you look into this function, the value of radius and the value of delta G will remain the same. Only the net free energy that is there in the system, that will reduce because this constant will be added into the system. And that is why
Vineet, sorry to interrupt you. I had a class with this user ID at 8:50.
Just give me 2 minutes.
Yeah, please.
So what you observe over here is that delta G for heterogeneous is much lesser than the delta G for homogeneous, which I explained earlier also, that delta G for homogeneous requires around 25%, whereas delta G requirement for heterogeneous is around 10%. So these are the references that I used, and thank you very much.